Today I'll be talking about this class of states called neural network quantum states. And the work that I'll be presenting will be in collaboration with Antonio Mezzacapo from IBM, Giuseppe Carlo from the Flatiron Institute, as well as Titus Neupert, which is my supervisor. Okay, so I'll first briefly describe what we mean by neural network quantum states. So basically, neural networks are just highly parameterized functions or maps where we give the network some input and the network spits out some output. So the output can be like a single vector or a vector of numbers. And similarly, the wave functions are also just functions or maps from the Hilbert space to some complex amplitude. So given a basis vector, the wave function simply assigns a complex amplitude to this basis vector. And the idea of neural network quantum states is then very straightforward. So basically, we simply want to think of the neural network as representing the wave function. So we give as input to the network some Hilbert space configuration, and then we apply a series of linear and nonlinear transformations to the vector. So these W's here are some matrices which we apply onto the Hilbert space configuration. And then we apply some nonlinear transformation, and then this is sort of like a feed-forward neural network. And if you do it in an alternating sequence, you can, in some sense, if the networks are large enough, you can, in principle, capture any kind of function. So since we want to represent a complex wave function amplitude, there are two ways that we can do that. So one way is simply to use complex weights for the matrices so that the output would naturally be complex. But this can sometimes lead to optimization problems because the complex functions are not so well behaved and there could be some singularities. And the alternative is actually to use real parameters, but have the network output two outputs, one for the amplitude and one for the phase. So we tried both approaches, but it's not completely clear which parameterization is better. So the idea to use this kind of neural networks as variational wave functions was originally introduced by Carlo and Troyer in 2017 in their science paper. And at that time, the network that they chose was called this restricted Boltzmann machine. In this type of network, we have a binary spin. So we have hidden spins as well as the visible spins. And these visible spins will correspond to the physical degrees of freedom that you actually want to model. So for a given configuration of visible spins and hidden spins, you can assign an Ising type energy. So basically, this sort of like an Ising model, a classical Ising model, which are where the visible spins and the hidden spins are interacting. And it's restricted in the sense that the hidden spins and the visible spins are not interacting directly. So given this kind of energy, you can, using the Boltzmann distribution, define a probability distribution for the hidden and visible spins. And because it's restricted, you can marginalize over the hidden spins, and you can get a very simple analytical form for the wave function. Okay, so with some simplifications, actually this restricted Boltzmann machine is just very similar to a one-layer feed-forward network with a hyperbolic cosine activation function. Okay, so using this type of network, they applied it to solve this 2D Heisenberg model on the square lattice. And so there is no sign problem here. So you have exact quantum Monte Carlo results. And so on this y-axis is the relative error to the ground state energy, and the x-axis is the sort of the hidden unit density. So it's the number of hidden units divided by the number of visible units. So larger alpha here just means a more complex network, which is more representative. And using this RBM, they managed to get pretty good results on this 10 by 10 Heisenberg model, and it's comparable to the state-of-the-art tensor network results at that time. So of course, I think now there are better tensor network results, but I think as a first result, it was already quite encouraging. Okay, so since Sandro already mentioned about all this variational Monte Carlo optimization procedure. I will be quite fast on this part. So basically the problem that we are trying to solve is given some variational wave function that depends on, let's say, the parameters W, we want to find the parameters W that minimizes the energy expectation value. So you can estimate the energy expectation value using a Monte Carlo averaging. If you see that the energy can be written in this form, where you have some local energy which can be very efficiently evaluated if the Hamiltonian is sparse. And then this term here is just a probability distribution. So if you can obtain a sample coming from this probability distribution, then averaging the local energy over a sample from this probability distribution, you get a sort of estimate of the energy. And in the same way, you can also compute the energy gradient with respect to the different parameters of the wave function. And this OK here is just some logarithmic derivatives, and all these expectations you can also evaluate in using Monte Carlo. And the idea then is just simply to do a gradient descent and walk down the energy landscape by updating in this form. So this is just like a stochastic gradient descent. So of course you can also use other more advanced optimizers like Adam or something like that. But basically the idea is just using the gradient to update and lower the energy. But the approach that we usually take is actually to use the method that was introduced by Sandro maybe 20 years ago, which is called stochastic gradient descent. So the idea is just that, as he already explained, but let me just briefly describe it. So is that the different parameters of the wave function are not completely equivalent, in the sense that some parameters are more important than others, and this is captured in this S matrix here, which is sort of like a correlation matrix or the Fisher information in a machine learning community. And if we change our update rule into this form, so where we solve for this delta P, and we update according to this formula, but using the delta P instead of directly the gradient, then this in some sense realizes some sort of imaginary time evolution. And this is the method that we usually use for our optimization, because we generally find that this method gives a much smoother and a faster convergence as well. And of course, there's some added computational cost because you need to solve this matrix. But if you use sort of like some sparse solvers or like conjugate gradients or something, going to like 10,000 or more parameters is still very feasible. Okay. Okay, so now I briefly mention about a package that we have been working on. So this is the package that we are called Netket that we've been working on which provides tools for exploring these neural network quantum states. So beyond the main feature of like finding ground states of Hamiltonian, there are also more recently other tools such as like a quantum state tomography, where we given some observations of a state, we try to find the best wave function that reproduces those observables, as well as unitary time evolution and open quantum systems. And in the more recent versions, we are also adding support for PyTorch as well as JAX. Okay. So this package has a very simple Python interface, and in the latest soon-to-be-released version, the backend is also completely written in Python, which makes it very simple if you want to extend and modify the code for your needs. So for example, to do a variational Monte Carlo calculation, one only needs a few lines of code, and here we are solving the 1D Heisenberg model with a very shallow network called the RBM, and with just a few lines of code, we can already get quite reasonable results, and both the energy and the energy variance can be converging quite well. Okay, so now I move on to the first application of these neural network quantum states that I want to talk about. So it will be on frustrated spin models. So in particular, we will be looking at this very famous model called the J1, J2 Heisenberg model on the square lattice. So this is given by this Hamiltonian, where we have nearest and next nearest neighbor spin-spin interactions. So it is frustrated in the sense that you cannot satisfy both the nearest neighbor and next nearest neighbor interactions simultaneously. If you have both J1 and J2 positive, then they both want to sort of anti-align the spins, and you just cannot satisfy both conditions at the same time. So in this sense, it is frustrated. So it's an open problem where the phase diagram is not completely agreed upon. So in the extreme limits, the phases are known. So for small J2, we have this new ordered state where we have this sort of like checkerboard configuration. And in the large J2, we have some kind of striped ordered phase. But in the middle, which is also the region of maximum frustration, it is not completely clear whether there is a spin liquid phase, and even if there's a spin liquid phase, it's not completely clear what is the nature of that phase, whether it's gapped or gapless. So this is a hard problem because there's a sign problem. So quantum Monte Carlo is not very helpful. And it's also in 2 dimensions. So DMRG is also not highly efficient. Okay, so there has been a lot of computational work on this model. So we also wanted to see how well these neural network quantum states can perform on this model compared to other methods, sort of like as a benchmark, since there's a lot of other works to compare to. So for this problem, we decided to choose a deep convolutional network. So this is the network architecture. There's a 6-layer deep network. It's a fully complex network with a single complex valued output. And also, since we are choosing the network to be completely convolutional at every layer and there's no dense layers in between, the network is also completely translationally invariant, which is very helpful for the optimization. In addition, we also impose a C4 symmetry simply by summing over the rotations of the configuration. And this omega here, this is just some a character which allows us to choose the ground state symmetry sector, which is also important because the ground state is not necessarily in the trivial sector. And this also allows us to choose, let's say, if we are interested in looking at excited states or something like that. Okay. So regarding the choice of this neural network, one of the key reasons for using this deep convolutional network is actually discussed in this paper by a group in Israel, where they found that actually deep networks are more efficient in capturing entanglement as compared to shallow networks. And by efficient, I mean that there's less parameters are required. So in this paper, they actually derive some analytical bounds for the entanglement entropy, like here, where L is like the depth of the network, K is the kernel size, and N is the system size. So D is the dimensions of the system. So if we want to have a volume law entanglement, we will want the entanglement entropy in, let's say in 2D, then the entanglement entropy should be N squared. So given this condition, so what they found is actually that using this formula, you can see that the number of parameters needed for a volume law state would be order N if you're using a deep convolutional network. But for let's say a single layer network like a RVM, you will need like order N squared. So in this sense, it is polynomially more efficient than shallow networks. So these are the analytical results, but practically, actually, we also do see that the deep networks are much more efficient. So if we look at the Heisenberg J2 equals 0 limit, where we can get exact quantum Monte Carlo results. So I show again here the result of the science paper of Carlo and Troyer, where they use a 1-layer network, and this was the result that they got. And if we use our deep network with about, let's say, 500 parameters corresponding to about alpha equals 5 here, we see that we almost have a 1 order of magnitude improvement in the accuracy already. And and this was just a 6-layer deep network. And in fact, other people have tried even deeper networks and like, let's say 10 or 20-layer deep autoregressive models from the group in Israel. And they managed to improve the accuracy even by 1 more order of magnitude. Okay, so before moving on to the frustrated case, so far we only look at the Heisenberg limit, but before moving on to the frustrated case where J2 is more than 0, I would like to first discuss a little bit about the sign structure of the wave function. So at the extreme limits, the sign structure is actually known. So the wave function can be written in this form, where psi is now a purely positive number, and then this and we have this sign factor here, which is a plus or minus 1, depending on the number of up spins on the rate sides. So if the number of up spins on the rate sides are even, then we have a +1 factor. Otherwise, we get a -1 factor. Okay. And so in the new phase, we should look at the rate sides will be like a checkerboard, and in the stripe phase, we have to choose it like alternating columns. So the reason this is important is because it's much harder to do the optimization when we do not impose these prior sign structures. So for this work, we actually added this prior sign structure, but we still let the network be completely complex so that in principle, it can change the sign structure. So in our calculations, we usually try both limiting sign structures and pick the one that gave the better energy. So, okay, going back to the J1, J2 problem, we measure the spin-spin correlations or the structure factor. And in the new phase, where for small J2, we expect that the pi-pi correlations to be large, and this corresponds to the checkerboard configuration. On the other hand, in the large J2 limit, we have the pi zero correlations should be large, corresponding to the stripe phase. And we can see that actually the results used on this, let's say 6x6 lattice using the convolutional network is actually not so bad, and the general trends are at least reproduced. But of course, you can see larger deviations from the ED results closer to the frustrated region as I expected. Okay, moving on to a larger system size beyond ED. So here we are looking at this 10 by 10 cluster, and we now compare with other variational approaches such as DMRG with the matrix product states as well, and also more traditional VMC wave functions, which is based on this pair product fermionic wave functions. And these results were very kindly provided by Francesco Ferrari and Federico Becca. So in this plot, I show the energy obtained relative to our network. So if the point is above, it means that our network is better, and if it's below, it means that our network is worse. So, so quite encouragingly, it seems that we see that the network is performing better in almost all regions in the phase diagram, except in the frustrated region where we see that the DMRG results are still better. But at the very least, it seems that these neural network states do give sort of competitive results throughout the phase diagram. Okay, so one important caveat that I should mention is that whereas these fermionic wave functions as well as the matrix product states, they have this SU2 symmetry, the neural network wave function that we use actually do not have this, it's not SU2 invariant. So this J1, J2 model is SU2 invariant, and the ground state should be in the S equals 0 singlet sector. But if we actually measure the total spin, we see that actually the total spin that we get is not 0. So in the regions where the performance is better, we do get a better or lower total spin. But especially in the frustrated region, the total spin that we measure is actually quite high. So I mean, there's still a substantial overlap with the S equals 0 sector, since the next eigenvalue will be like at 2, corresponding to the triplet sector. But this is definitely a significant problem that needs to be addressed. I mean, if we somehow can capture this symmetry, it seems likely that the performance can improve much more. And in fact, there is some development in this aspect, and there's a group in Belgium where they actually found a parameterization of the Hilbert space, which would allow one to capture this total spin symmetry. So this SU2 symmetry exactly. So yeah. And a second problem that that we encounter could be related to the sign structure. So although there's no sign problem in the sense of quantum Monte Carlo, there's an issue that is actually very difficult for the network to pick up the correct sign structure. So there was some investigations into this problem by a group in Cambridge, and I think he's going to give a talk about it later. So they were looking at this kind of network where they have two different networks. One is the amplitude network and one is the phase network. And what they found was actually that the sign structure that the network learns, even at the J2 equals 0.5 limit, is actually almost exactly the same as the Marshall sign rule. So it's not really not really learning the correct sign structure even in the frustrated region. And I also should mention that the results that I'm showing is already like at least a year old, and there were some recent updates, and there have been some work from people using this type of RBM times a pair product wave functions. And so in this work here by Yusuke Nomura and Imada, they actually look at the phase diagram of this J1, J2 model by considering the level crossings between the different excited states. And I think the author, Yusuke, will be giving a talk about these findings later. Okay, moving on to the final application, and I'll be quite fast here. In quantum chemistry, so it's a quantum chemistry problem that we wanted to try to apply our machinery to. So basically, in quantum chemistry, the problem is usually in let's say a continuous system as opposed to having particles on a lattice. But since we want to apply the same kind of machinery, we'll map this fermionic Hamiltonian to a spin Hamiltonian. So there have already been 2 talks about it where they use a slightly different approach. But the approach that we took is this second quantized approach where we have a finite orbital set. And if we fix this finite set of orbitals, the fermionic Hamiltonian will take, in general, this kind of form. And in order to use the machinery that we have already been working on, we decided to map it to a spin Hamiltonian via some kind of mapping. So of course, the most simple mapping is this Jordan-Wigner mapping. And there are also other mappings like the Bravik-Kitaev. So for instance, in the Jordan-Wigner mapping, it's a very simple mapping, but in the end, the resulting Hamiltonian will be non-local. Whereas in, let's say, the Bravik-Kitaev mapping, the final Hamiltonian will at least be quasi-local, where the operators have a log n support. So very quickly, this is just the Jordan-Wigner mapping that is very familiar to everyone. So basically, we map the creation and annihilation operators to these spin operators, but we need to keep track of the parity. So we have to add this string of this Jordan-Wigner string, which is non-local. Okay, so here is some of the results that we got on a very small molecule. So we have here's C2 and N2 on some minimal basis set. And we were just using a very simple network like the RBM. So it's just a very simple 1-layer network. And here we have the energy as a function of the nuclear separation. So this is just the dissociation curves. And the red line is the exact result that was obtained with FCI. And you can see in the zoom in that the green stars, which is corresponding to the neural network, actually performs a little bit better than one of the common quantum chemistry method, like the coupled cluster. Okay, so and another thing is also that we looked at is different mappings. So we try to compare whether different types of mappings have any impact on the result, because if you change the mapping, in some sense, you're also changing the wave function. So we compared 3 different types of mapping: the Jordan-Wigner mapping, as the parity mapping, as well as the Bravik-Kitaev the mapping. So while the Jordan-Wigner and parity are both extensive in the system size in terms of the size of the operators, the Bravik-Kitaev, as I mentioned earlier, is only log n in the system size. However, it seems like all the different mappings seem to give relatively the same result, and we get a relatively decent accuracy in despite regardless of the mapping that we use. And in order to further understand the performance of the RBM, we plot here the probabilities of the most relevant configurations in the wave function. And we look at the 3 different wave functions: the exact wave function, the blue, and as the neural network, which is the orange, as well as the CISD, which is basically just a wave function that only takes into account single and double excitations from the Hartree-Fock state. So looking at this plot, you can see that the RBM has support on configurations beyond the single and double excitation. And this is important in order to reach an accuracy where we can make a realistic chemical predictions. Okay, so next I'll look at some of the problems that that we encountered during our simulations. So when we tried to scale up to much larger basis sets, we actually found that there's a significant drop in performance, and the performance is strongly related to the number of samples that we use in Monte Carlo. So this is quite a big problem, because the number of samples that we require to reach a high accuracy is increasing very, very much with the system size. And this will present a very big computational cost if we want to move further. So, and one of the problems is that the wave functions that we are trying to sample from is actually has very extreme distribution. So here is a sort of like a sample wave function, and you can see that most of the weight is in one or two configurations. So this makes the sampling, the metropolis sampling of the wave function extremely challenging. And we are recently exploring a little bit on some ways to overcome this sampling problem. So since and what we tried to do was to actually sample from, let's say, instead of sampling from psi square as normal, we sampled from psi to the beta. And here we see that actually by sampling from this bias sampling, we actually do see some interesting improvements, and we get like, there's sort of like a minimum where optimal point where sampling from psi to the 0.5 seems to give better results. But this is just on a very small system, and it's still sort of something we are working on. And okay, so that's the end. And to wrap up, I want to just say that so we were looking at the performance of these neural network states on two different types of problems. First, we look at the frustrated magnetism on the J1, J2 model, and also quantum chemistry on some small basis sets. And lastly, if you're interested, you can also check out the code that we were using at this website. Okay, thank you.